All right, welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are going to dive into the concept of the Hessian matrix, and then we'll also look at the quadratic forms, how we can transform a quadratic form into a matrix. All right, now let's try to have a little knowledge about the Hessian. Actually, the name is Ludwig Otto Ludwig Otto Hess, right? The name is Ludwig Otto Hess. This is the name. This is the man we are calling Hessian. This is his full name, Ludwig Otto Hess, or you can call it Hess or Hess. So this is where the Hessian comes from. His, and it came as Hessian, right? So he lived around 1811 to 1874. That was his lifespan. And this man basically worked in algebraic geometry and differential calculus. he his contribution was so massive in mathematics, right? So Hessian is a very good contributor in the world of mathematics. All right. Now, when we talk about Hessian mathematics, Hessian matrix, right? What does it mean? Okay. So Hessian matrix is basically a square matrix, right? That focuses on the second order partial derivative of a scalar valued functions. Okay, so what does this tell us? It tells us how the function curves in multiple directions and extremely useful in optimization, quadratic forms, and multivariable calculus. Okay, so this is how it helps us in our world of mathematics. It helps us to in optimization, multivariable calculus, and quadratic forms. Quadratic forms. Okay, so you know, in abstract algebra, we are interested in the quadratic forms. Optimization, when it goes to the economics aspects, optimization in economics, it's very helpful. And this is basically for calculus, right? Multivariable calculus. Okay, now it has a formal definition of which I'm going to give it out here. I'm going to give a formal definition. So the Hessian matrix is well defined as, you see, we are talking about second order partial derivative, right? So we defined it as this die squared f with respect to x1 squared, die squared f with respect to x1, die x2, up to die squared f with respect to die x, die Sn, right? Then we have die squared f with respect to die x2, die x1, die squared f with respect to die x2, x squared, right? x2 squared up to die squared f with respect to die s2, die xn, and then the last row, die squared f with respect to die xn, die x1, die squared f with respect to die Sn, die x2 up to the squared f with respect to die xn squared. Okay, so this is a square matrix. All right. And note, the Hessian matrix is always symmetric. Okay. So it is always symmetric if F is twice differentiable. It is always symmetric if F is what? Twice differentiable, right? That is, the mixed partials, the mixed partials are equal. What I mean is that, what I mean by the mixed partials is that, when you differentiate with respect to x, and then the next time you differentiate with respect to x, y, you differentiate with respect to x, the next time you differentiate with respect to y, and also if you differentiate with respect to y, the next time you differentiate with respect to x, these functions are the same. This is what meant by mixed partials. With respect to x, y is equal to with respect to y, x. So it is always symmetric if it is twice differentiable. That is, the mixed partials are what? Equal. That is what we have here. So this is basically the same as di squared f over what? Di x1 di x2 equals what? Di squared f over what? Di x2 di x1. This and this are equal, right? You can either use this notation or that notation. Okay, so now, why is it so important for us to study the Hessian matrix? Okay, why is it important? One, it helps us to determine the concavity and the convexity of a particular function. Okay, so let's note that down. So the importance of the Hessian matrix, one, it helps us to determine the concavity and or the convexity of a function. That is one. Two, it also helps in Newton's methods. It is used in what? Newton's methods for multivariable functions. So it is used in Newton's methods for multivariable functions. Three, it is very useful in quadratic forms. And these quadratic forms actually helps us in the abstract algebra. Okay, so it is used in quadratic forms. It helps us with the quadratic forms. So in quadratic forms, let's say a function of x equals x to the t ax, where a is what? Where a is the Hessian matrix. Where a is the Hessian matrix. All right. So these are the few importance of the Hessian matrix or the Hess matrix. All right. So now that we know the importance and we know a little bit over the Hessian, then let's try to look at some structured examples that will help us to determine the Hessian matrix. Right. Okay, so example one, you want to determine or you want to find a Hessian matrix from this particular function. This is a function of two variables, right? So f of x and y equals x squared plus 3xy plus 4y squared, right? So how do we determine the Hessian matrix out of this? Okay, so basically I needed to introduce this, right, in the overview. Basically, the Hessian matrix, denoted, we normally denote this as h of the function is equal to, this is a 2 by 2, right? So is fxy, fyx, fyy. So this is how we determine the Hessian matrix. First element on the first row is the second derivative with respect to x. Second derivative fxy, and the first element on the second row is what? Fyx. The third element, the second element on the second row is fyy. Okay, so let's look it out from this example. So from here, we know that our fss, our first derivative will be 2x plus 3y. We are differentiating with respect to x, so differentiate x squared, we have 2x, differentiate 3xy, we have what? 3y with respect to x. Okay, because we are dealing with respect to x, 4y squared will be what? A constant, which is what? 0. So now we have the first derivative, right, with respect to x. So the second derivative with respect to x will be equal to what? 2, right? You differentiate 2x, you have what? 2. This tends to what? Constant, which is 0. So fxx is what? Is 2. Now, we have to determine fyy, or let's first find fxy. So fxy will be equal to, we have fx here, right? We have fx here. So to determine fxy, meaning that we are going to differentiate this fx with respect to what? Y. So if you differentiate fx with respect to y, you're going to have what? 3, right? This tends to constant. This differentiate with respect to y, you're going to have what? 3. Now, let's differentiate respect to y from the original function. We're going to have what? 3x plus 8y with respect to y. Okay, with respect to y, the second time, we're going to have what? 8, right? With respect to y, this goes to 0. Then we differentiate, we have what? 8. Now we differentiate with respect to yx. So yx, we're going to have what? Yx, we're going to have, we are differentiating this with respect to what? X. So we're going to have what? 3 as well. So what we said earlier, that the mixed partials are equal, is what we are seeing here. Consider fxy is equal to what? Fyx. So fxy is equal to what? Fyx, which is equal to 3. So this element will represent what? The off diagonal. This element will represent what? The off diagonal. And then the second derivative with respect to x and with respect to y will represent the main diagonal. Okay, so we have our Hessian matrix to be equal to fxx is 2, fxy is 3, and fyx is also 3, fyy is also 8, right? So this is our Hessian matrix from this function. Okay, so that is how we obtain the Hessian matrix out of a function, right? That is how we obtain the Hessian matrix out of a function. Very simple, very, very simple. So Let's look at another example. So example 2. Example 2, we have f of x and y equals x squared plus y squared, right? So we want to determine the Hessian matrix out of this. Okay, so this we are going to differentiate with respect to x. We're going to what? 2x. Then the second time with respect to x will give us what? 2. Then we come to fxy here with respect to what? Y. We're going to have what? 0. Then we come to fy of this function. We have what? 2y. Fyy, we're going to have what? 2. Right? Then fyx, we're going to have what? This one with respect to what? X, we're going to have what? 0. You see, it's very simple. Very, very simple. So our Hessian matrix, the Hessian matrix denoted as h of x will be equal to our fxs is what? 2. Our fxy is what? 0. Our fyx is also 0. And our fyy is also what? 2. Right? So this becomes our Hessian matrix. Right? So determining the Hessian matrix given a function is very simple. Just have to focus on the second partial derivative of the function. If you have two variables, basically it deals with two variables, right? So x and y. So it differentiates x 2 times, differentiates y 2 times, right? Then you find the mix of each. You find fsy, you find fyx. So it is symmetric because the mixed partials are equal. The mixed partials here are the fxy and the fyx. So you can see that all our results, the mixed partials are equal. All right, so that is how we determine the Hessian matrix given particular function. All right, now let's move on to a structured examples where we will be asked to determine or find the critical point. 2, where we'll be asked to find the Hessian matrix. 3, where we will be asked to, classify them as whether local minima, local maximum, or saddle points. Right. Let's get into that. Question number 2, we also need the critical point and want to determine whether it's a local minimum, maximum, or saddle point, right? So with the critical point, step 1, with the critical point, we find partial with respect to x, and that will be what? 2x. Partial with respect to y will be what? Minus 2y, right? So if you want to know the critical point, set both to 0. So we set this to 0, we're going to have what? X equals what? 0. Set this to 0, we're going to have what? Y equals what? 0. Right. So the critical point is at 0, 0. Right. Once we know the critical point, we want to know that where it is stretched towards the minimum, maximum, or saddle point. So before we can do that, we have to determine the Hessian matrix, right? So with that, we know that the Hessian matrix, of which is fxy fyx and fyy, we have to determine the second order partial derivative, right? So from here, we know that our fxx will be equal to what? 2. Our fyy from here will be what? Negative 2. Our fxy will be what? 0. And our fyx will be equal to what? 0 as well. So our Hessian matrix, h of f, will be equal to 2, 0, 0, 2. Right? So this is our Hessian matrix. One is negative, right? So this is our Hessian matrix. Now we know the Hessian matrix. This is a diagonal matrix. So if you want to determine whether it is a local minimum or local maximum or saddle point, you have to check the eigenvalues. This is positive, this is negative. So meaning it is a saddle point. Let me take it again. This is a diagonal matrix. So the eigenvalues are the main elements, the main diagonal elements. And we have one to be positive, one to be negative. So meaning this function is at the saddle point, because we are seeing one element to be negative, one element moving on the other side, one side, and the one element is also moving on the negative side. So it is a saddle point. We don't know whether it is curved upwards or down. So it is basically, it is a saddle point at 0, 0. Don't forget, if you state this, then you have to include the critical point. So it is a saddle point at 0, 0. That is the critical point. Okay, it is a saddle point at 0, 0. Right? Because one eigenvalue, one eigenvalue is positive and the other is what? Negative. One is positive and other is negative. Right? So that is why this is at the saddle point. Once again, if you have a diagonal matrix and you want to determine whether it's a local minimum, maximum, or saddle point, then the work is going to be easy, because the off diagonal have 0 elements, right? 0, 0. So if that is the case, then the main diagonal element becomes the eigenvalues. And one thing you have to know is that if both eigenvalues are positive, then you can boldly say that it is at the local minimum. If both are negative, then you can say that it is at the local maximum. If one is negative and one is positive, then you can talk about saddle points. So that is example 2. Example 3, this is the problem that we have. And we want to determine the critical points and also determine whether it is at the minimum, maximum, or saddle point. Okay, so now the critical points, right? So solution, step 1, the critical points. We know that we need the first partial derivative, right? So with respect to x will be what? 4x cubed minus 4y, right? So this is with respect to x. With respect to y, we're going to have 4y cubed minus 4x. So these are the first partial derivatives. We need the critical point. So we set both to 0. So set both to 0, right? So when we do that, that means that 4x cubed minus 4y is equal to 0. So we're going to have 4x cubed equals 4y. So basically, this is telling us that we have x cubed is equal to what? Y. So let's consider that as equation 1. So we consider this as equation 1, or we can rewrite it and say y is equal to what? S cubed, equation 1, right? Then we set this 2 to 0. We have 4y cubed minus 4x equals 0. So we're going to have 4y cubed equals 4x. So we have y cubed equals what? X, right? So this tells us that we have equation 2. Now, we can see that from equation 1, we have y equals what? S cubed. And equation 2, we have y cubed is equal to what? X, right? So if y is equal to x cubed and y cubed is equal to x, then it means that we can substitute wherever we see y, we can substitute wherever we see x, we can substitute y cubed, right? So let's try to rewrite this well. We can have x equals what? Y cubed. So we name that equation 3. So equation 1 is y equals what? S cubed. And equation 2 is what? X equals what? Y cubed. So wherever we see x in equation 1, we put what? Y cubed. Right? So um, so put 1 into what? 2. Put 1 into 2. So we're going to have x cubed to the what? 3 equals what? X. X cubed all to the 3, right? Because we are saying that s cubed is what? S cubed is equal to y, and y cubed is equal to what? X. Equation 3. Equation 2, right? So if that is the case, then we are putting equation 1 into what? Equation 2. So wherever we see y in equation 2, we put what? S cubed there. And that is what we have here. So y, we are putting s cubed there. So we have s cubed to the 3. Already it has a power of 3. So all power 3 equals what? X. So we're going to say that we have x to the 9 equals what? X. Right? So basically, we are going to have s to the 9 minus what? X equals what? 0. Right? So this, we are going to have x to the 9 minus x equals 0. We factor x out, we have x to the 8 minus 1 equals 0. Right? So we have either x equals 0 or 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 x to the 8 minus 1 is equal to 0. Right? So we have first value here for x equals 0, or x to the 8 minus 1 equals 0. So this means that x to the 8 is equal to what? 1. So this basically means that when you take cube root on both sides, 8th root, right? So that is going to be a plus or minus, because this is an even number. So we're going to have x equals what? Plus or minus square root of what? 1. So you have x is equal to what? Plus or minus 1. Right? So that is what we have for x. Okay, that is what we have for x. So this tells us that x is either equal to 0 or x is equal to plus or minus what? 1. So what do? We have to substitute the corresponding values of what? X into what? Either equation 1 or 2 to find the values of what? Y. So if we have y equals s cubed, then if s is equal to 0, y will be what? 0 as well. So we have our first critical point to what? 0, 0. And also if x is equal to 1, then y is equal to what? 1 as well from here, right? Then it means that our second critical point will be what? 1 and 1. Okay? And also if x is equal to -1, then means that our y will be what? -1 as well, because -1 cubed is what? -1. So our third critical point is at -1, -1. Interesting, right? So these are the critical points for this particular function: 0, 0, 1, 1, and -1, -1. So therefore, that's the critical points. The critical points are 0, 0, 1, 1, and -1, -1. Okay, so these are the critical points to this particular question. Now we want to determine whether it is at the local minimum, at the local maximum, or at the saddle point, right? Now, this is the case where we have 3 critical points. So it means we have to determine the whether it is at the local minimum, maximum, or saddle point. Then it means we have to take each critical point, okay, and do that. So at 0, 0, then we have to find the Hessian matrix for at 0, 0, right? So let's try to find the partials, right? So we're going to have 4x cubed minus 4y. So fxy will be equal to -4, and also fxx will be equal to 12x squared, right? Now fy will be equal to 4y cubed minus 4x, right? So fyx will be equal to -4 as well. Okay, fyy will also be equal to 12y squared, right? So we have the Hessian matrix to be fxx is what? 12x squared. fxy is -4. fyy is 12y squared. fyx is also -4, right? So we have the Hessian matrix. Now, how do we know that it is at the local minimum, maximum, or saddle point? So we consider the point at 0, 0. We're going to substitute into this, and then we're going to have what? Fxs to be what? 12 into what? 0, which is equal to 0. And fyy will be equal to what? 0 as well. right? So we have 0 here. So this means that our exact Hessian matrix will be what? 0, neg 4, neg 4, 0, right? So this is our exact Hessian matrix. So now, this is what we have. How do we know that it is at the local minimum or local maximum or saddle point? We have to determine the eigenvalue, right? So the eigenvalue for this is going to be what? 0 minus what? 16. And that is what? Equal to 0. So we have um, 0 minus lambda minus 4 minus 4 minus lambda, right? So the eigenvalue is going to be minus lambda times minus lambda plus, so this is going to be what? Minus 16 equals what? 0. So we have lambda squared equals what? 16. So this means that lambda is equal to plus or minus what? 4, right? So our eigenvalue is plus or minus what? 4. So this means that at 0, 0, we have saddle point. So at 0, 0, we have a saddle point, right? So this is for at 0, 0. Now let's determine at 1, 1. Okay. So at 1, 1, that means that fxx will be equal to what? 12 into 1, which is equal to what? 12. Fyy will be equal to 12 into 1 squared, which is equal to what? 12. So our Hessian matrix at 1, 1 will be equal to what? 12, neg 4, neg 4, 12, right? So this, we can see clearly that this is going to be at the minimum because all the eigenvalues are positive. Should we do that? Okay, if you want us to do that, we can do that for you to see. So this one, the eigenvalue is going to be what? 12 minus lambda minus 4 minus 4, 12 minus lambda, right? So we're going to have, if you find the determinant of this, we're going to have 12 minus lambda, 12 minus lambda minus 16 equals what? 0, right? So we're going to have 144 minus 12 lambda minus 12 lambda plus lambda squared equals what? Minus 16 equals 0. So we're going to have lambda squared, then this and this will give us minus 24 lambda plus 144 minus 16 equals 0, right? So this is basically lambda squared minus what? 24 lambda plus 128 equals what? 0. So this tells us that This tells us that lambda is equal to 16 or 8, right? So we have the eigenvalue to be what? 16 and 8. So we can say that they are all positive. So it is at the local minimum. So at so at 0 0, no, at 1 1, it is at the local minimum, because all the eigenvalues are positive, right? At 1 1, it is at the local minimum because all the eigenvalues are positive. We have what? Lambda equals 8 and lambda equals what? 16. Right. So at 1 1, we have what? At local minimum. Now the final uh, case we have to check is at what? -1 and -1. So we have to check that one as well. Don't forget that at -1 and -1 too, we will have local minimum. This is because Fy is equal to what? 12x squared. And Fxx is also what? 12x squared. Yeah, 12y squared and 12x squared, right? So this means that at -1, -1, we are going to have what? 12 into -1 squared, which is what? 12. And this is what? 12 into what? -1 squared, which is what? 12, right? They are all positive. So since they are all positive, it's not going to change the eigen values. They are all going to be what? 8 and 16 again, right? So we can boldly say that we can boldly say that we can say that at -1, -1, it is also at the local minimum because all the eigenvalues are positive. That's lambda equals 8 and lambda equals what? 16. Right. So that is the process you go through to determine the critical point, and it also determine whether it's at the local minimum, maximum, or saddle point. We have alternative way to also determine the minimum, maximum, or saddle point. Now, you can use the determinant approach. So another way is to use the determinant. So if you find the determinant of your Hessian matrix and it's greater than 0, and also the FSS is also greater than 0, then you can say that it is at local minimum. And if the determinant is greater than 0 and FSS is less than 0, then you can see that it is at what? Local maximum. So local maximum. But if you find the determinant, if the determinant is less than 0 and FSS is greater than 0, then we can say that it is at the saddle point. If the determinant is less than 0 and FSS, which is the second order partial derivative with respect to x, is less than 0, then you can see that it is at the saddle point. That is an alternative way to also determine the local minimum, maximum, or the saddle point. Okay, so that is for this particular question. Now, let me give a trial, right? So let me give with this example, we want to find the critical point. Then we go ahead to find the Hessian matrix. Then we determine whether it is at the local minimum, maximum, or saddle point, right? So this is what we have to determine the critical point first. So step 1, to determine the critical point, differentiate the function with respect to x. You're going to have what? 2x, right? And also with respect to y, you're going to have what? 2y, right? Set this to 0. Set both to 0, right? So if you set both to 0, meaning that fx is equal to 2x is equal to what? 0. So meaning x is what? 0. Set fy equals 2y equals what? 0. Meaning this implies that y is equal to what? 0. Okay, so our critical point for this particular function is at the critical point is at x comma y equals what? 0, 0, right? So our critical point is at 0, 0. Now we know the critical point. What is next? We want to find the Hessian matrix. Okay, so step 2. From our previous class, we know how to find the Hessian matrix already. So you know that you have to find the second partials, right? So fxx is going to be what? 2. fxy is going to be what? 0. And then fyy is going to be what? 2. fyx is going to be what? 0 from here. So therefore, our Hessian matrix is going to be 2, 0, 2. So this is our Hessian matrix. So once we have the Hessian matrix, what do we need next? We want to determine whether it is a local minima, maxima, or saddle point. So to determine that, then it means we have to first we have to check the eigenvalues, right? To know whether it is minima, maximum, or saddle point, we have to check the what? The eigenvalues. We have approaches. We have two approaches, right? We have where we can use the determinant, and we have where we can use what? The eigenvalues. Okay. So if you want to use the eigenvalues, so that is step 3, right? So this is our Hessian matrix. So h of x, h of f is what? Given as this. Now, is it local minima or local maxima or saddle point? So the step 3 is going to tell us that. Now, if you have a diagonal matrix, okay, if you have a diagonal matrix, then to determine the local maxima or the minima or the saddle point, focus on the eigenvalues, right? So if it is a diagonal matrix, then the eigenvalues are the main diagonals. So the eigenvalues are 2. They are all 2. They are all 2, right? And they are all positive. If they are all positive, then it means that this function is a local minima, right? If they are all positive, then it means that this function is at the local minima, right? So here our eigenvalues are what? 2 and 2. So it means that the function is at the local minima. That is an alternative way of determining whether a function is at the local minima, maxima, or saddle point. Okay, so let me give you these tips. So if all are positive, then it is a local minimum. That is 1. If all are negative, then it is a local maxima. And if one is negative and other is positive, then it is what? A saddle point. Okay, but if you have one to be 0 and other to be non-zero, or if you have all to be 0, then you cannot conclude, or you cannot, it's inconclusive, right? So you have to do further further follow-up, right? So these are what you have to know. If all eigenvalues are positive, then it is a local minimum. If all eigenvalues are negative, then it is a local maximum. If one is negative and the other is positive, then it is what? A saddle point. Take note. If all eigenvalues are positive, then it is a local minimum. If all eigenvalues are negative, then it is a local maximum. If one is negative and the other is positive, then you can talk about saddle point. And also, if one is 0 and the other is non-zero, you cannot determine whether it is maximum, minimum, or saddle point. You have to do further test. 5. If all are 0, if all are 0, you cannot also determine whether it is maximum, minimum, or saddle point. So take note. But what you can determine is what we have here. All right, so you have to know this. Now, let's come to the eigenvalue side. You know, if you have a diagonal matrix, is just like you have A0, 0, D, right? Meaning the up diagonal are all 0 and the main diagonal is what? A non-zero. That is what we mean by diagonal matrix. So if you have a diagonal matrix, Then the main diagonal element will help you to determine whether it is a local minimum, maximum, or saddle point. So if all the values here are positive, then it is a local minimum. If all the values here are negative, then it is a local maximum. If one is negative and one is positive, it is a saddle point. Okay. Now, if one is 0 and the other is non-zero, you cannot conclude. You have to do further tests, right? By looking at the signs of the second derivative, the second partial derivative. Okay. What if all are 0? Then it means that you have to also do further tests by looking at the signs of the second derivative, second partial derivative. Okay. So we can see clearly from here that this is a what? A local minimum, because all the eigenvalues are what? Positive. Okay. So we note this. We know this. So we know that it is a local minimum, right? At where? At what critical points? At what? 0, 0. Don't forget, the critical point was 0, 0. So it is a local minimum at what? 0, 0. That will be the conclusion, right? So once again, don't stress yourself finding the eigenvalue to determine whether it's a local minimum, maximum, or saddle point. Note, if you have a diagonal matrix is a matrix that has non-zero, that has non-zero at the main diagonal, but up diagonal are all 0. The up diagonal are all 0, right? So that is what we mean by a diagonal matrix. If you have something of this nature, then you can easily determine the where the function is being stretched towards, right? So let's take example 2. Let's take example 2. With example 2, we have f. Okay, so the last example on how we can determine the critical point and determine whether it's at the local minimum, maximum, or saddle point. I want to leave this example with you. You know, we have this function, okay, and we want to determine the critical point and determine whether it is at the local minimum, maximum, or the saddle point. Okay, so try to work your way out. I want to give the final answer out. So the critical point will be at 0, 0, and it will be at the saddle point. It will be at the saddle point. So if you do your work well, you're going to have the critical point go 0, 0, and it will be at the saddle point. So please do your best to work it out. And if you get it, give me a thumbs up at the comment section. All right, so let's move on to the quadratic forms. The quadratic forms where we'll be given a function and a constraint, and we would want to determine the eigenvalues and also find the maximum value and the minimum value. So we are going to look at all that in the quadratic forms. So when we talk about the quadratic forms, okay, the quadratic forms in abstract algebra is basically an expression of the form is an expression of the form k of x equals x to the t ax, right? Where A is a symmetric matrix, x is a vector in Rn, where Rn can be R squared, R cubed, and all that, right? And x to the t ax is a scalar output, right? Okay, so basically, the quadratic forms that we talk about, maximum and minimum values, they basically correspond to the largest and smallest eigenvalues of the symmetric matrix. Okay, so if you talk about maximum and minimum values, they are basically the largest and smallest eigenvalues that we obtain from that quadratic form, right? So the largest value is the maximum value, and the smallest value is the minimum value. Okay, so note that the largest eigenvalue the largest eigenvalue is the maximum value, and the smallest eigenvalue is the minimum value. Okay, mostly, or quadratic forms they goes with a constraint, right? So in mathematics, when we talk about constraint, it's especially in calculus, optimization, and abstract algebra, is basically an inequality or an equation. Okay, it's basically an inequality or an equation that restricts the values of the variables. Is an inequality or an equation that restricts the values of the variables. Okay, so a constraint adds a restriction on x, such as if you have x to the t ax, such as x to the tx equals 1, this constraint basically means that we can only consider vectors on the unit sphere, right? Or what we call the circle, the unit circle in two-dimensional. So this means that we can only consider vectors in the unit sphere or the unit circle in the two-dimensional. This is the constraint that we are talking about. So it's an inequality or an equation that restricts values of the variables. So that is all about constraint and quadratic forms. That is what you need to know before we proceed in solving problems. Okay, so let's consider our first problem where we want to determine the where we want to express a certain quadratic form in matrix notation and determine whether it is minimum, maximum point using the constraint, a particular constraint, right? So we are going to start with that, and then dive from a 2 by 2 matrix before we move on to a 3 by 3 matrix, right? So let's get into it. Okay, so our first example is we want to express the following quadratic forms in the notation, in the matrix notation, right? A x to the t ax, where A is a symmetric matrix. Hence, we want to determine the minimum and maximum point using the constraints. This is our constraint, right? This is our constraint. X1 squared plus x2 squared equals what? 1. And the problem is x1 squared plus x2 squared plus 4x1 x2. Okay. Now, we have the B, right? But I want us to finish with the A first, then I'll go on with that. Okay. So we know that we have been given a constraint, right? So we have been given this particular constraint. So given x1 squared plus x2 squared equals 1. This is our constraint, right? And we have been given the quadratic form, right? As q of x1, x2 equals what? X1 squared plus x2 squared plus 4x1, x2, right? So this is the quadratic form that we have been given. Okay, under this constraint, right? So before we get into it, I want you to know this is because we are seeing x1, x2, just x1 and x2, meaning that we are going to form a 2 by 2 matrix, right? Now, I want you to know the structure of the 2 by 2 matrix off head. You have to know that. If you know that, then transforming the quadratic form into a matrix won't be a problem. It's going to be the most easiest thing you do in abstract algebra, okay? So if you want to do that, note that the 2 by 2 matrix have these elements, right? The 2 by 2 matrix have this element A1, 1, A1, 2, A2, 1, and A2, 2. I'm sure you are aware of this, right? You know this element very well. Okay. I thank God you know that. So if you know that, then I want to tell you that this we have here, our main diagonal elements, A11 and A22, are basically what have been expressed in x terms, right? So this is telling us this is our x1 squared is our what? A11. Those squared stuffs you see there are the main diagonal elements. So if you see A11, it should tell you that it's what? X1 squared. It represents, that element represents what? The x1 squared. And the A22 represents what? X2 squared. So take note. The A11 is equal to x1 squared, right? And to determine the value of A11, then you have to look at the coefficient of what? A1 squared, x1 squared, right? So the coefficient that we see in here, which is 1, is going to be what? A11. So we are interested in the coefficient of the quadratic forms. Nothing more, nothing less. So in here, the coefficient of x1 squared becomes A11. And that is what? 1. And the coefficient of x2 squared becomes what? Our A22. So A22 is what? Also 1. And that is the coefficient of what? X2 squared. Now, we have identified our x A11 and A22, which is the main diagonal elements, right? Now, we need the A12 and A21. How do we get that? Well, from Hessian matrix, we learned that the cross partial, right? The mixed partials, which is fxy is equal to what? Fyx, right? We learned that. Good. So if we know that this is equal to this, then it means that x1, x2 is equal to x2, x1. Let me take it again. From Hessian matrix, we learned that the mixed partials, the Hessian matrix is always symmetric, right? And in here too, we are talking about symmetric matrix. So if in the Hessian matrix, it is always what? Symmetric, and the twice differential of what? The function is what? Which is the mixed partial derivatives are equal, then it means that fxy is equal to what? Fyx. Are you getting the whole argument? So if that is true, then we can bring that on board here. We are having x12, right? So this basically means that x12 is equal to what? X21. It's just a notation, right? X12, x1, x2 is the same as x2, x1. And that notation is the same as a12 equals a21, right? This notation, they are just notations. This is x here, and we have what? X1, x2. It's a. It's basically a1, x2. It's the same notation. It's just that we are using a in here and we are using x in the quadratic forms, right? So x1, x2 is basically what? A1, 2. And s2, x1 is basically what? A2, 1, right? And we know that this and this are the same. So if they are the same, then it means that any coefficient that we see there at x1, x2 will be divided or will be shared for these two elements. Are we getting the whole argument? So that means that our a12, a21 will be equal to 4/2, which is equal to what? 2. Because the coefficient of x1, x2 is what? 4. We divide that by 2 to have what? 2, which is going to represent a12 and what? A21 in the matrix. I hope you get this argument. It's not anything difficult. So one thing I want you to know is that note the element in the 2 by 2 matrix. If you note that, the rest is going to be very easy. Because if you know that in the 2 by 2 matrix, you have a11, a21, a11, a12, a21, and a22, then don't forget, first row, first element on the first row represents your what? X1 squared. Second element, that's the second element on the second row represents your what? X2 squared. And then your A12 represents your what? X1, X2, which is the same as what? X2, X1. And that is the same as what? A21. So if you have X1, X2, then means that your A12 is going to be what? 0.5, because you're going to divide 1, the coefficient here, into 2, right? To have for A12 and to have what A21. So we're going to have 0.5, 0.5. I hope argument is clear. So we're going to say that our matrix is going to be what? 1, 2, 2, 1. From this explanation, we see that our x1 is 1, which is the A11. and our x2 squared is also, the coefficient is also what? 1, which we have here. And therefore, the x1, x2 has a coefficient of what? 4, of which we are going to divide it for both a12 and what? A21. So we divide 4 into 2 and we share it here on the off diagonal. So that is what we have on here, 2, 2. I hope this explanation is cool. Okay, so now we have determined the matrix, right? We have been able to transform the quadratic form into a matrix, into a symmetric matrix. So let's say that this is A, which is the symmetric matrix. So we have gotten our symmetric matrix from the quadratic form. Next, we want to, determine whether it is at the local. We want to determine the minimum and the maximum points. The minimum and the maximum what? Points, right? So if you want to do that, then we have to express in matrix form, right? We have to express whatever we have in the matrix form. So we're going to say that, okay, so we already have the matrix representation. So we have to find the eigenvalues to be able to determine whether it is, to be able to determine the minimum and maximum points, right? I already told you that the minimum point, the maximum point represents what? Your largest eigenvalue, and the minimum point represents what? The smallest. The minimum point represents your smallest eigenvalue. So let's go ahead and do that. So we have our matrix, right? So we can say that let x equals what? X1, x2, right? And then we can say that we have 1, 2, 2, 1, right? Multiplied by x1, x2, which should be equal to what? 0, 0. We are not yet here with this, but I just want to state it down. Okay, so we have to find the eigenvalues to be able to determine the minimum and the maximum point. So the eigenvalues we are going to find the determinant of the matrix, right? You know that to determine the eigenvalue, this is what we have to do. So lambda I should be equal to what? Lambda 0, 0, lambda, right? So we're going to take this from the matrix. So we're going to have what? A minus lambda I to be equal to what? 1, 2, 2, 1 minus lambda 0, 0, lambda, right? So we have this minus this. We have 1 minus lambda, 2, 2, 1 minus what? Lambda. So we need to find the determinant of this. So finding the determinant of that, we're going to have what? 1 minus lambda, 2, 2, 1 minus what? Lambda. So this should be equal to what? 0. Okay. So we're going to do that here. So we say that 1 minus lambda into 1 minus lambda minus 2 into 2 should be equal to what? 0. So 1 minus lambda plus lambda squared is minus 4 equals what? 0. So we're going to have lambda squared minus 2 lambda minus 3 is equal to what? 0. So this is telling us that our lambda is going to be lambda is equal to -1 and lambda equals what? +3. Okay, so we have lambda equals -1 and lambda equals what? +3. So this clearly tells us that our maximum point or our maximum value is at lambda equals 3 and our minimum value is at what? Lambda equals -1. As I already said from the previous so the maximum value is at lambda equals 3 and the minimum value is at lambda equals -1. Okay, now we have been able to determine the minimum and maximum values, right? Now, what is next? We want to know so we want to normalize this function, right? So before we can do that, we have to find the eigenvalue. We have to find the eigenvectors, right? So to find the eigenvectors, we know that for lambda, we have to take each lambda, right? So for lambda equals 3, our eigenvectors is going to be what? 1 minus what? 3. Don't forget that we had 1 minus lambda, 2, 2, 1 minus what? Lambda, right? So our eigenvectors is going to be 1 minus 3, and then we have 2 here, 2, 1 minus what? 3, right? This multiplied by some unknown. So let's say V1, V2. Because we are dealing with eigenvectors, I love to choose the variable V1 and V2, right? You can choose as well X1 and X2, doesn't matter, right? So this should be equal to what? 0, 0, right? So this we're going to have -2, 2, 2, -2, right? Multiplied by V1, V2 equals 0, 0, 0, right? So this is what we have. Now, we want to know V1, we want to know V2, right? So we form an equation of which we are going to have -2V1 plus 2V2 equals what? 0, and that is equation 1. And then we have 2V1 minus 2V2 equals what? 0, that's equation 2, right? So clearly we can see that equation 1 and equation 2, they are all the same. So we cancel out 1 and then deal with only 1. So we're going to have -2V1 plus 2V2 equals what? 0. So this means that we're going to have what? 2V1 equals what? V2. 2V2, right? So we have V2 equals what? V1. So we assume values, right? So but we don't just assume any value, we assume a sensible value, right? In mathematics, the easiest value to work with is 1. So we normally use 1 if we are doing this kind of assumption, right? So if V1 is equal to 1, then V2 will be what? 1 as well. So our eigenvector for corresponding to eigenvalue 3 is 1, 1, right? So we can say that our eigenvalue, the eigenvector corresponding to eigenvalue 3 is 1, 1, right? So this is our eigenvector, right? So what do we need next? We need to normalize this eigenvector, right? So to do that, we find the magnitude of this result. So the magnitude of this is going to give us what? Square root of 1 squared plus 1 squared, right? So we're going to have what? Square root of 2, right? Now, we use this magnitude to divide this result. So the normalized result will be equal to 1 over square root of 2, 1, 1 here. So this is basically telling us that we have 1 over square root of 2, 1 over square root of what? 2, right? So this is our normalized value. So we can go here, and say that um, the norm at the maximum value is equal to what? This, right? And our conclusion will be this way. Therefore, the maximum value, the maximum value, which is lambda equals 3, occurs at 1 over square root of 2 and 1 over square root of 2, right? So this is our conclusion. Therefore, the maximum value, which is lambda equals 3, occurs at 1 over square root of 2 and 1 over square root of 2. So it means that we have to check for lambda equals -1 as well. So for lambda equals -1, our matrix, right? We're going to have 1 minus minus 1, 2, 2, 1 minus minus what? 1. So we're going to have this multiplied by some unknowns. So I'll have to use V1, V2, right? So we're going to have 2, 2, 2, 2, right? So this multiplied by V1, V2 equals what? 0, 0, right? So here we also see that 2V1 plus 2V2 is equal to what? 0, is equation what? 1. And 2V1 plus 2V2 is equal to what? 0, equation 2, right? So clearly from here as well, we can see that this equation is equal to what? This equation. So we cancel 1 and there was only 1. So right, so we're going to do that. We use equation 1 equals 0. So we're going to say that 2v2 is equal to what? Negative 2v1, right? So we have v2 is equal to what? Negative v1, right? So this we have here, v2 is equal to what? Negative v1, right? So this equation, look, we don't just determine any value we can't just pick any value and say that this is v1, this is v2, or this. You have to be very smart, right? So in here we say that, in normal sense, we know that we count from 1 to what? Infinity, right? So meaning 2 is greater than what? 1. So if you are doing this kind of assumption, you have to always say v2 equals what? v1, right? So that if v1 is 1 and it's 2 times of this, then v2 will be what? 2. You get a point? So here we're going to say that if v1 is equal to positive 1, then v2 will be equal to what? Negative 1. Are we getting the argument? v1 is equal to positive 1. Then it means that v2 will be what? Negative into what? 1, which is what? Negative 1. So this means that our eigenvector is what? Positive 1 and negative 1. Right? Are we getting the whole argument? Probably you can't tell me that you have v1 equals what? v2. It has to be what? v2 equals what? v1. That is the idea. So if this is 1, then this is also 1. But if this is 2 and it's something like v2 is what? 2 v1, then it means that if v1 is 1, then v2 would be what? 2 times of 1, which is what? 2. So get this clear. Don't wait, just position anything just like that. If v1 is 1, then v2 will be what? Negative 1. So here, our eigenvector, the eigenvector corresponding to eigenvalue -1 is 1 and -1, right? Now, we have to know where this thing occurs, right? So we have to normalize this. So doing that, we have to find the magnitude of what? This, which is going to be what? 1 squared times plus -1 squared, and that is what? Square root of what? 2, right? So we divide this eigenvector by the what? The magnitude, and that is going to be what? 1 over square root of 2 right? And this is equal to 1 over square root of 2 -1 over square root of what? 2, right? So this is what? Our normalized values, eigenvector, right? So we're going to conclude that therefore the minimum value, which is lambda equals -1, occurs at v1 equals what? 1 over square root of 2, and v2 equals what? -1 over what? Square root of 2. Simple. So that is the process we go through to determine the minimum and the maximum values and where they occur, right? So that is the process. This is basically the 2x2 problem. So we can as well have a 3x3 problem, of which is going to be a lot of work. It's going to be a lot of calculations. So yeah, so I'll give one example so that we try it out. Okay, so example 2 on x1 x2, where you form a 2 by 2 matrix, I want to give a trial work, right? So once you are done, leave your solution at the comment section, right? So let's look at the trial. So this is a trial work. You're going to result into a 2 by 2. So before I leave and move on to this kind of problem that will result into a 3 by 3 matrix, I want to give you this strong tip. Please, for this kind of work to be so much easy for you for transforming this quadratic form into a matrix notation, please learn this for the 2 by 2. A11, A12, A21, A22. Okay, please learn this. If you are not ready to learn any abstract thing, you learn this. Just learn this. So note, A11 is equal to x1 squared is equal to the coefficient of x1 squared if available. If available. If it is not, if x1 squared is not available, then it means that A11 is equal to what? 0. If the coefficient of, if x1 squared is not available, then it means that A11 is what? 0. This part is 0. If x1 squared is not available, then A11 is what? 0. But if it is available, then the coefficient becomes what? A11. Okay. I hope you've written your example down. Try it out. Let me continue from here. Right. A12 is equal to the coefficient. Okay, let me finish with this one first. A22 is equal to the coefficient of x2 squared if available. But if it is not available, then A22 is equal to 0. Right? If x2 squared is not available, then A22 is what? 0. Get the point? Okay. Now, A12 is equal to what? A21. Right? A12 is equal to what? A21. And that is the coefficient of what? That is the coefficient of what? The cross of x1 or x2. So that is x1, x2, the coefficient of this. So if the coefficient of this is what? 4, then means that you are going to share for A12 and A21. So that is going to what? 2. So that represents what? A12 and what? A21. Take note. So these are the basic things you need to be able to work your way out when it comes to this kind of problems. So we continue with the 3 by 3 cases. All right. Okay. So with this problem of which we are going to result into a 3 by 3 matrix, with this as well, this is what I want you to know before we begin the journey. Okay. So this is the problem. We want to express this 9x1 squared minus x2 squared plus 4x3 squared plus 6x1 x2 minus 8x1 x3 plus x2 x3 in matrix notation, right? X to the x, ax, where A is a symmetric matrix, and we want to determine the minimum and maximum point using the constraint. So this is our constraint. Okay, so from the beginning, we talked about the constraint, and we know what all is about, right? So here we know that solution, we are given a quadratic form of x1, x2, and x3, right? So and that is equal to 9x1 squared minus x2 squared plus 4x3 squared plus 6x1 x2 minus 8x1 x3 plus x2 x3, right? We want to transform this into a matrix, right? And then find the minimum and maximum points, okay, under this constraint. Okay, so first of all, what I want you to know is the elements in the 3 by 3 matrix, right? We know that when you have a 3 by 3 matrix, then the elements in that matrix are A11, A12, A13, A21, A22, A23, and then we have A31, A32, A33. These are the elements in the 3 by 3 matrix, right? So this is the quadratic form that we have been given, right? So I want you to learn something very simple from here. From the 2 by 2, we learned it, but I want to mention it here again. You see, this is our main diagonal, right? This is our main diagonal. The A11, A12, A22, and A33. They are the main diagonal elements, right? Okay. So when it comes to the quadratic form, the elements that will represent the main diagonal are the elements x1 squared, x2 squared, and x3 squared. The coefficients of these elements will represent what the main diagonal, right? So x1 squared basically means a11, x2 squared basically means a22, x3 squared basically means a2, a3, a33, right? Okay, so what are we going to use to represent them? So the coefficient of x1 squared is a11. The coefficient of x2 squared is a22, and also the coefficient of x3 cube is a33. Okay, so this is what you have to know. The rest is just addition and subtraction. So you know that x1 squared, the coefficient of x1 squared is what? A11. The coefficient of x2 squared is what? A22. The coefficient of x3 squared, S3, S3 squared is A33, right? So basically, that is the main diagonal element. Okay, now we are done with the main diagonal element. Let's come to the elements on the upper half and the lower half of the matrix. Okay, so when you have A1, 2, you know that from Hessian matrix, we know that fxy is equal to fyx, right? From Hessian matrix. Okay, so same way in here, A12 is the same as A21. Okay, A12 is the same as A21. So the same idea from the 2 by 2, we are going to use the same thing here. So if you have A12 is the same as what? A21. So in the quadratic form, that will be the x1, x2, right? X1, x2. Okay, so if you have x1, x2 is the same as x2, x1, right? So the coefficient of x1, x2 or x2, x1 becomes what? The value of what? A1, A2, A1, 2, and A2, 1, right? So you have the coefficient of x1, x2 to be 1. Then it means that you have to divide it by 2 to have what? 0.5. And that will go for A21 and A12. Are we okay? So let me clean the problem. So the coefficient of x1, x2 is equal to x1, x2 is equal to x2, x1. Okay? And the coefficient of these elements, okay, are, when you divide it by 2, then you have what? The value for what? A12 and A21, right? So if, for instance, the coefficient over here is 1, you divide it by 2 and you have what? 0.5. So you share it for this and this. So meaning that A12 is what? 0.5 and A21 is what? Also 0.5. That is how we do it. So if you know the elements in the 3 by 3 matrix, then nothing is going to be difficult again. Okay. Now, you left with A13 and what? A31. So don't forget, A13 is equal to what? A31. There is no changes, there is no difference. So the same way, when you come to the quadratic form, x1, x3 is the same as x3, x1. Okay, so if you have x1, x3, then the coefficient that you have there, divide it by 2. And then the result you have, share it among what? This you have here. So if the coefficient of x1, x3 is 1, then it's going to divide by 2, have what? 0.5. So 0.5 you share for what? A13 and A31, because they are all the same. Okay, now we are done with that. A32 and A23, they are all the same, right? So A23 is equal to what? A32. So if you have When you come to the quadratic form, that is what we call the x2, x3, and that is equal to what? X3, x2, right? So if the coefficient of x2, x3 is 1, then it means you have to divide it by what? 2 to have what? 0.5. Then you share it for what? Both x2, x3 and what? X3, x2. And that represents what? A23 and A32. Very, very simple, right? So now let's form the matrix out of this explanation that I've given out. Okay, so this is the quadratic form that we have. Cube of x1, x2, x3 equals 9x1 squared minus x2 squared plus 4x3 squared plus 6x1 x2 minus 8x1 x3 plus x2 x3. Okay, so this is the quadratic form that we have. So as I said earlier, the squared represents your what? Your main diagonal. So x1 squared, x2 squared, x3 squared represent your what? Main diagonal. So we're going to have that. So our x1 squared, the coefficient is what we are interested in. So the coefficient of x1 squared represents our a11, and that is what? 9. So we have 9 here. X2 squared is what? The coefficient over there is what? -1, and that represents what? A22. So we have -1, right? The coefficient of x3 squared is what? 4. So we have the last element on the main diagonal to be what? 4. Good. So what is next? We need to find the upper half and the lower half of the matrix, the element there. So we interested in what? A12. We know that A12 is basically what? The x12, x1, x2, x1, x2. And the coefficient over here is what? 6, right? So we divide 6 by what? 2, and we have what? 3. So we're going to share x1, this 3 for what? X1, x2, and what? X2, x3. X1, X2, and what? X2, X1. Because X2, X1, and X2, X1, X1, X2, and X2, X1, they are all the same. So we share the coefficient that it possesses for all. So this here, the coefficient is what? 6. We divide it by 2 and we have what? 3. So we share the 3 for the 2. And this here, you know that it represents what? A12 and A21. So we have what? 3, 3, right? Then we come to A13, right? The A13 basically represents what? The x1 and x3 in the quadratic form, right? So in the quadratic form, what we have here is what? -8x1, x3, right? Which is the same as x3, x1, right? So the coefficient we have here, we divide it by 2. So -8 over 2, which is what? -4. So this -4 goes for what? X1, x3, and what? X3, x1, which represent what? A1, A13, and what? A31. So we have what? -4, -4, right? Then we come to the last part, which is A23 and what? A32. So that also goes for what? X2, x3, right? We know that x2, x3 is the same as what? S3, x2, right? So the coefficient over here, which is 1, we divide it by 2 and share it for all. So we're going to have what? 1 divided by 2, which is what? 0.5. So 0.5 is for what? A2, 3, and what? A3, 2, because they are all the same. So we have 0.5 and what? 0.5. I hope that is very simple, right? I've broken it down into simpler uh, ways for everybody to get it clear. Okay, so now we have been able to transform the quadratic form into a matrix form. Now, once we have that, I want to make it so simple so that even the basic, the hardest way of the hardest those who are learning from the scratch will even get it, right? This thing is not anything difficult, right? So here, now that we have the matrix, okay, now that we have the matrix, what do you have to do? Can I clean this? Okay, this is going off. So let's say that our matrix is what? A. So we have the matrix, which is 9, 3, 4, 3, 1, 0.5, 4, 0.5, and 4. Right. Okay. So this is the matrix that we have been able to form out of the quadratic form, right? So what we have to do next is to just express that matrix. We want to determine the minimum and the maximum points, right? So we have to find the eigenvalues. Once we have been able to determine the matrix from the quadratic form, then we have to find what? The eigenvalues, right? To be able to determine the minimum and the maximum values of the constraint. Okay, so we have to determine the eigenvalues, and we know how to determine the eigenvalues. So we know that determinant of the matrix minus lambda what? I to be what was 0. So it means that we have to subtract lambda I from this matrix and then find the determinant equated to 0 to find the eigenvalues. So lambda I will be equal to lambda 0, 0, 0, lambda 0, 0, 0, lambda, right? So we're going to subtract this from this. Okay, so we're going to do that. So a minus lambda I will be equal to, let's do it straight away. 9 minus lambda is going to be what? 9 minus lambda. Then this part will remain the same, 3, 4. Then we have 3. Then we have minus 1 minus lambda. So we have minus 1 minus lambda. Then we have our 0.5. Then we have negative 4. Then we have 0.5. Then we have 4 minus lambda. Okay, so this is our a minus what? Lambda I. So we want to find the determinant of this. So determinant of that to equal to what? 0. So find the determinant of 9 minus lambda, 3, 4, 3, 1, lambda, 0.5, 4, 0.5, 4 minus what? Lambda. So we find the determinant and equate it to 0 to find the eigenvalues, right? So here we're going to have, we are using the row 1, right? So that would be 9 minus lambda multiplied by 0.5, 4 minus lambda minus 3 multiplied by 3 neg 4, 0.5, 4 minus what? Lambda plus negative 4 multiplied by 3 neg 4, negative 1, negative lambda, 0.5, right? So this is what we have. So we're going to find the values. We're going to find the values of that. So we're going to have 9 minus lambda multiplied by minus 1 minus lambda, 4 minus lambda minus this times this. 0.5 times 0.5 is 0.25, right? 0.5 times 0.5, 0.25, right? So we have 0.25, right? So we are done with the first part. Okay. Then we come to minus 3 into this time. This is 3 into 4 minus lambda. Then we're going to have 4, negative 4 times what? 0.5. So that will be what? Minus 2. And minus 2, this one is affected by what? Negative. So that will be what? Plus 2, right? Then minus 4 into 3 times 0.5 is what? 1.5. Then negative 4 times this. So that will be what? Positive, plus 4 into negative 1, negative lambda, right? So this all should be equal to what? 0. Okay, so let's break it down. We have 9 minus lambda into this times this is minus 4. This times this is plus lambda. This times this is minus 4 lambda. This times this is plus lambda squared minus 0.25, right? Then minus 3 into 12 minus 3 lambda plus 2 minus 4 into 1.5 plus, so that will be minus 4 minus 4 lambda, right? And that is equal to what? 0. Okay, so now we can go ahead and simplify 9 minus lambda into minus 4 minus 0.25, right, is 4.25. So minus 4 plus minus 0.25 is minus 4.25. So we have minus 4.25. Then lambda plus minus 4 lambda is minus 3 lambda. So we have minus 3 lambda plus lambda squared, right? Then we have minus 3 into 12 plus 2 is 14 minus 3 lambda, right? Minus 4 into 1.5 minus 4, right? That is negative 2.5. So we have negative 2.5 minus 4 lambda. and that is equal to what? 0. Okay, so let's go out up here. So when we go up here, we're going to have 9 minus lambda into minus 4.25 minus 3 lambda plus lambda squared minus 3 into 14 minus 3 lambda minus 4 into minus 2.5 minus 4 lambda, and that is equal to what? 0. Okay, so now we have to expand each bracket and then simplify. So 9 times negative 4.25, that will be 38.25. So we have 38.25, right? Then 9 times minus 3 is minus 27 lambda. 9 times lambda squared is plus 9 lambda squared, right? Then minus lambda times minus 4.25 is plus 4.25 lambda. Then minus lambda times minus 3 lambda becomes plus 3 lambda squared. Then minus lambda times lambda squared becomes minus lambda cubed. Okay, so we are done with the first set. Move to this section. Minus 3 times 14 is minus 42. So we have minus 42. Then minus 3 times minus 3 lambda becomes plus 9 lambda. Okay, so we left with the last part. So minus 4 times minus 2.5 is plus 10. Plus 10. Then minus 4 times minus 4 lambda becomes plus 16 lambda, and that is equal to what? 0. Okay, so we have all this. We have to simplify, right? So now we have minus lambda cubed here. So we're going to have minus lambda cubed. Then we add all lambda squared, right? So 9 lambda squared plus 3 lambda squared becomes 12 lambda squared, right? So we have plus 12 lambda squared minus 27 lambda plus 4.25 lambda plus 9 lambda plus 16 lambda becomes, that also becomes plus 2.5, 2.25 lambda, right? That becomes plus 2.25 lambda, right? And okay, and minus 38.25 plus minus 42 plus 10 becomes plus 70.25 equals what? 0. Okay, so that is the quadratic, this is cubic equation. So this, when we try to avoid the negative in front of the cubic, we're going to have -1 divided here, -1 divide here, -1 divide here, and -1 also divided. So you have what? Lambda cubed minus 12 lambda squared minus 2.25 lambda plus 70.25 equals 0. Okay, so this is our quadratic, our cubic expression that we have to simplify and find lambda, right? So this is not a rational expression, so we can't use we can't test. If we try to test, let's say lambda equals 0 and see if it will be a we will have a factor, it's not going to work, right? So we have to use calculator and go away, right? Or we have some formula called Candone's formula or Candone's method. It's going to be very complicated, so try to use your calculator to get your lambda, lambda 1, lambda 2, and lambda 3, right? So we go up here. We go up here, then we say that lambda cubed minus 12 lambda squared minus 2.25 lambda minus plus 70.25 equals 0. So when you solve this using your calculator, you have lambda to be equal to, please try to use the full decimals that you had, okay? Because if you don't use the full decimal that you have, you're going to short when you are finding the eigenvectors, all right? So first value is going to be 11.67751396, right? And lambda 2 will be equal to 2.6192577372, and then lambda 3 will be equal to negative 2.29677130. Okay, so with these values, okay, from the earlier, from the beginning, I made mention that the largest value, the largest eigenvalue is your maximum value, right? And the smallest eigenvalue is your minimum value, right? So from here, the largest eigenvalue is what? 11.677513, right? So our maximum value, the maximum value is 11.677513, and the minimum value is negative 2.29677130. Okay, you can decide to run it to have negative 2.30 for the minimum value and also have a 11.68 for the maximum value. But make sure that you use the full value when you are computing the eigenvectors. Otherwise, you have different values for the eigenvectors. Let me mention it again. You can run your value for the for your maximum value and your minimum value, but Note, if you are going to find the eigenvectors, make sure that you use the original value that you had for the maximum value and the original value that you had for the minimum value to obtain your eigenvector. Otherwise, you'll be having uh, error, right? You have some small minor errors, right? Okay, so now that we know our eigenvalue and we know our maximum and minimum values, then it means that we have to find the eigenvectors to be able to normalize our function, right? And know where the maximum value occur and know where the minimum value also occurs. So we have to find the eigenvectors, right? So in doing that, we have to consider the maximum value and find the eigenvector for that. And also we come back and consider the minimum value and find the eigenvector for that. So for lambda equals 11.6775139, we're going to substitute that value into wherever we see lambda in this matrix. Then we find the eigenvector, right? So we're going to have that to be 9 minus 11.677. So 9 minus 11.6775139, 3 neg 4, and then neg 4, -1 minus 11.6775139, then 0.5, and also minus 4, minus 4, 0.5, then we have 4 minus what? 11.6775139. Okay, so let's simplify this. So when we simplify this, you're going to have 9 minus 11 points. 9 minus 11.6775139 will give us negative 2.6775139. Then we have our 3 minus 4, our 3, then minus 1 minus 11.6775139. We're going to have negative 12.6775139. Okay, then we have our 0.5 there. And the last one is minus 4, 0.5, then 4 minus 11.6775139 is negative 7.6775139. Right. So this is the simplified matrix. So we are going to multiply this by an unknown, right? So we're going to have this negative 2.6775139, 3 neg 4, 3 negative 12.6775139, 0.5, then we have negative 4, 0.5 -7.6775139. So this is the matrix that we have. Okay, so we're going to multiply this by some unknowns, right? So let's do it from here. So we multiply that by V1, V2, V3, and that is equal to 0, 0, 0, right? So this is a whole lot of decimals, right? That is why it's taking us that far. So this, we're going to form three systems of equations with three unknowns, right? So we're going to have minus 2.6775139 V1 plus 3V2 minus 4V3 equals 0, and that is equation 1. Then we have 3V1 minus 12.6775139 V2 plus 0.5 V3 equals what? 0. And that is equation 2. Then we have minus 4V1 plus 0.5 V2 minus 7.6775139 V3. And that is what? Equation 3. Okay. So we're going to solve equation 1, equation 2, and equation 3 simultaneously to find V1, V2, and V3. But what we have to do is that we have to try to use either substitution or elimination method, okay? So we're going to use elimination method in here, right? So what we are going to do is that we are going to multiply equation 2 and equation 3 by 4 and 3 respectively. So we're going to multiply equation 2 and equation 3 by 4 and 3 respectively, right? So when we do that, it means that we're going to multiply here by 4, and 3 by 4 is what? 12. When you multiply 4 by what? Negative 4 by 3, you're going to what? Minus 12. So when we add this, we're going to go as 0. So the V1 will go off. So that is the elimination method. Okay, so I can clean this off. So here, when you multiply equation 2 and equation 3 by 4 and 3 respectively, we are going to have 12V1. So minus 12 times 4 minus 12.6775139 times what? 4 will give us minus 50.7100556 V2, right? Then 0.5 times 4 will give us plus 2V3, and that is what? Equal to 0 for equation what? 4. Okay, we do same process for equation 3. We are going to multiply it by what? 3. So when you do that, you're going to have minus 12V1, then 0.5 times what? 3 is 1.5. So we have plus 1.5 V2. Then minus 7.6775139 times 3 times 3 is minus 23.0325417 V3, and that is what equal to 0 for equation what 5, right? So we have equation 4 and equation 5, which has V1 and V2 that can be eliminated, right? So our aim is to eliminate V1 so that we can solve for V2 and V3. So adding equation 4 and equation 5, we're going to have, when you add 12V1 minus 12V1, you're going to have what? 0. So the V1 section is off, right? Now, minus 50 points, minus 50.71005556 plus 1.5 will give us minus 49.21005556 V2. Then the last part is going to be what? Minus 23.0235417 plus 2 will give us minus 21.0325417 V3, and that is equal to what? 0, right? So we added V1 and V2, but V1 and V1 with from equation 4 and 5, right? But this is positive and this is what? Negative. So V1 had 0. And then we added minus 50.7100556 V2 plus 1.5 V2, and we had minus 49.2100556 V2, right? Then we added 2V3 plus negative 23.0325417 V3, and we had minus 21.0325417 V3, and that is equal to what? 0. So this is what we have. Now, we need V2 or V3, right? So here we can say that V3 is equal to 21.0325417 divided by 49.2100556 V2, right? So we made V3 the subject from this equation. You know, we have minus 49.2100556 V2 minus 21.0325417 V3 equals 0. And we made V3 the subject. So we had this. Okay, so let's try to divide that. So 21.0325417 divided by negative, divided by, that will be positive, right? Divided by 49.2100556. We're going to have V3 to be equal to 0.42740331 V2, right? So this is what we have, an expression in terms of V2. So we have 0.42740331 V2, right? So let me clean up this section. So we can see that V3 is equal to 0.42740331 V2. So here, what we do is that we assume values, right? And the best value to assume for is 1, because 1 is the easiest number to work with. So here we say that if V2 is equal to 1, then V3 will be equal to what? 0.427400003314, right? So we have V2 and we have what? So we're going to substitute V2 and V3 into equation 1 to have our V1, right? So when we do that, we're going to have minus 2.2967 V1 plus 3 into 1 minus 4 into what? This, which is 0.4274003314 equals 0, right? So we're going to send all this to this side. So we have minus 2.2967 V1 equals 4 into 0.4274003314 minus 3, right? So we have our V1 to be equal to 4 into 0.4274003314 minus 3 all over negative 2.2967, right? So we're going to have 4 into 0.4274003314 minus 3 all over negative 2.2967, right? And that is going to give us V1 to be equal to 0.561843886. Okay, so that is the value of what? V1. So we can see that our eigenvector is giving us 0.561843886, and then our V1 is what? 1. Our V3 is also 0.4274003314. So this is our eigenvector for eigenvalue 11.677, 6.77, right? So here, let's continue from here. We have to normalize it, okay? So we have to normalize it, but before we can do that, we have to find the magnitude of this. So the magnitude of this will be equal to square root of, we have to normalize this eigenvector, right? So when we do that, find the determinant, the magnitude of that, we're going to have what? Square root of 1.49834292. So when you square root that, we're going to have 1.2241406746, right? So this is what we have as our magnitude. So we're going to take 1 over the magnitude for multiplied by this. Then we know the normalized value, right? So we're going to have this times 1 over the magnitude 1.2240678646, right? So when you do that, you're going to have this to be equal to 0.5618438 divided by 1 point. You're going to have 0.458997018, and then 1 divided by 1.22406786. We're going to have 0.8169481715. Okay, and then the last one is going to be what? This over 1 point, so 0.427403314 divided by 1.22406786, right? So that is also 0.34916635559. Okay, so this is our normalized values at eigenvalue 11.68 or 11.6777. So maximum value, the maximum value, which is lambda equals 11.68, occurs at 0.4589973008, 0.81869481715, and 0.3491663551519. Okay, so the maximum value, which is lambda equals 11.68, occurs at 0.458997308, 0.8169481715, and 0.3491663559. Okay, so we have been able to determine the maximum value and where it occurs. So we normalize it. So after normalization, we had this, right? So this is where it occurs. Okay, so the maximum value occurs at these values. All right. So you have to also do for the smallest value, which is the minimum value. So you substitute that into the matrix, then you find the eigenvector, and also you normalize that one, then the result you obtain becomes your where the minimum value occurs. Okay, so go through the same process and do for the minimum value, which is negative 2.29, negative 2.2967. Do the same process and get where it also occurs. Okay, so I'll leave this example with you. Once you are done with that, try this example as well. The second example, that is example 2. X1 squared plus x2 squared minus 3x3 squared minus 5x1 x2 plus 9x1 x3. This is 1. 2. X1 x2 plus x1 x3 plus x2 x3 as the constraint. The same constraint, okay? The constraint the constraint is x1 squared plus x2 squared plus x3 squared equals positive 1. This is the constraint. Okay, so I want you to deduce the matrix out of this and find the minimum and maximum values. Once you are done with that, normalize it and determine where the minimum value occurs and also determine where the maximum value occurs. Do for this and also do for this as well. Later on, we're going to solve this example and solve this example as well. So please, this is how the process goes. If you want to normalize a particular constraint, then it means you have to first, after transforming the quadratic form into a matrix, you find the eigenvalues. The eigenvalue, the eigenvalues that you obtained, the largest value becomes your maximum value and the smallest value becomes your minimum value. So once you have these eigenvalues, put each eigenvalue, the maximum value, into the simplified matrix, this, something like this, and then simplify it and find the eigenvector. Once you have the eigenvectors, use that eigenvectors to find the magnitude. So if you have eigenvectors like this, find the magnitude of this. You know how to find magnitude. Square of this plus square of this plus square of this. Then the result you obtain, take 1 over the result you obtain, use it to divide each of the item in the eigenvalue, eigenvector. The result that comes out becomes where that particular minimum or maximum values occurs. And that is how we deal with this kind of problems. Thank you very much. I really appreciate your time. Please don't forget to subscribe, share with your mates, and keep learning. On to the